So let's talk about this required practical about specific heat capacity. Now, I'm going to start off with a warning. Personally, I feel like this is the hardest required practical out of all of the sciences. Okay, this one is complicated with maths and all sorts, but we're going to get through it together, you and I. We're going to go through it bit by bit, and if you have to go back and watch this again to get a bit more of a grip on what's happening, that's completely fine. That's completely understandable because this is going to be difficult. But like I say, together we're going to get through it. So, that warning said, let's begin. This experiment is how you work out the specific heat capacity of a material. Okay, specific heat capacity. Now, we watched about this in previous videos about trying to calculate how stubborn a material was at changing its temperature. And you might remember it had a unit of joules per kilogram degrees C. You might also remember that it had a formula, delta E, so change in energy equals mass times the specific heat capacity times the change in temperature. Okay, so what we need to work out is we need to work out the value of C, the specific heat capacity. So this requires a little bit of rearranging. What we're essentially going to do is shift the mass and the temperature change over onto the other side. We are going to stick them just under there like so. If you remember back, we talked about equation triangles for this. They looked a little bit, oops, I need 3 lines. Looked a little bit like so. You have your delta E at the top, your temperature change at the top, your energy change at the top. You've got your mass, and you've got your specific heat capacity, and you've got your delta theta, your change in temperature, just here at the bottom. Now, we want to know what the specific heat capacity is, so it's going to be delta E over m delta theta. So, to write that down, that's going to be C, so that's the specific heat capacity equals delta E, so the change in temperature, over m, the mass, times delta theta, the change in temperature. So there are some things that we need to find out. We need to find out how the energy applied to a block changes over time. We need to find out how heavy it is and how the temperature changes over time. Okay, with me so far? So equipment you will need for this, you are going to need a timer, a voltmeter, an ammeter. Now, if you've not come across voltmeters for a while, voltmeters, they're the ones for measuring potential difference, which is the more up-to-date name of voltage, and ammeters are for measuring current flow in a circuit. Again, don't panic about this too much because we have a whole unit on electricity yet to come, a whole chapter about it. And this over here is a thermometer. Right. How do you attach this equipment together? So, this is a simplified version of it, and I've deliberately left the labels off to try and make this seem a little bit less complicated. Here we go. This grey bit, this is your metal block, because very often people choose to do this on metals, this required practicals, this metal block here. And a lot of the time people choose to do it, use a 1 kilogram block, simply because it makes the maths easier if you've set m mass to 1. Around the outside, there is an insulator of some kind. Now, why is there an insulator around the outside? Well, this whole experiment is going to be about heating this block up and seeing how the temperature changes over time. The last thing that you want is the temperature from the block leaking into the surroundings, dissipating into the surroundings, because it will make your readings all go wrong. This red thing here in the center, that is a heater, so it's an electric heater, and there is a hole drilled into the metal block and the heater is pushed in. Attached to that, we have our voltmeter just here for measuring potential difference across the heater, and the ammeter just here for measuring current in the circuit. And here at the top we have a 12 volt DC power supply. If a lot of that electricity stuff worried you, Again, like I say, don't worry, chapter 2, electricity, we're going to go through all this in minute detail. Okay, so if you remember back to what I was saying earlier about how to rearrange this, we need to know delta E, so how the energy, how much energy is applied to the block essentially, how heavy the block is times by the temperature change. So what you will find probably in the block you are using is that a small hole has been drilled with space for a thermometer to be added. So this here, that's your thermometer. Okay. Now you might be wondering what this horrible scribbling down here at the bottom is. You see this scribbling just here? That is water. Or you might use oil, maybe. And that's there to ensure that when the heater starts heating up the metal block, it conducts through any air gap between the thermometer and the metal quickly and efficiently. Right, that's the equipment setup. So what's going to happen is that this power supply is going to get switched on and the block will start to heat. Now you've obviously going to have weighed it beforehand to check that your teacher's telling the truth about it being a 1 kilogram mass block, but generally it just makes the maths easier if that's 1 kilogram already. So the bits we've got to keep our eye on are the change in energy and the change in temperature. Well, when you have turned on your heater, you can turn on your timer. Okay. And what you're going to do is periodically throughout the experiment, you're going to take some readings. So you are going to take the temperature of the metal block, essentially using the thermometer. And that is going to give us our delta theta. It's going to give us, this bit there. Now the delta E is a little bit more tricky to work out. So what you might have is you might be in a place, in a school, in an institution that has a thing called a joule meter. That's really straightforward to use. I've never worked in a place that's owned one of those, so I'm going to assume you're going to have to go the long way round. Job number 1 is we're going to have to work out the power of the heater. Now, if you remember, way back to my power video, I said one of the ways you could work out power was current times potential difference. Now again, if that didn't stick, don't panic, because again, this really is a chapter 2 equation. So what you're going to do is you are going to periodically take readings from your ammeter and voltmeter and multiply them together to work out the power. Okay, but that should remain fairly static as these things go. What we now need to work out is how much energy got transferred to the block. Okay. Now, if you remember back again to that same video, I mentioned that power equals energy transferred over time. Now, if we rearrange that to be a little bit more helpful, that means that energy transferred equals power times time. Power, I know because I worked it out by multiplying the current and the potential difference together. Time I know because all the way back here, I've hidden it, there it is, I have my timer running. Okay, so if you want to work out how much energy has been transferred to the block, you times the power of the heater by how long it was on. And you will get a table of results. Now the nice thing about rearranging this so that C equals delta E over M times delta, that's not a delta symbol, I was going to draw theta, delta theta, so the change in temperature, is that because mass is 1, so we're going to times delta theta by 1, essentially we can forget that that exists. And what you end up doing is you end up drawing a graph of energy transferred against temperature. Okay, so remember these are our two core factors up here, energy change and temperature change. And you will most likely get a graph that looks like this. So energy is being applied, and then it will go up like that. And you may possibly get a slightly weird flat section here at the start. Now the reason why you got a weird flat section is that there is a lag between the energy being output by the heater and it getting through the metal, through the water, and to your thermometer. Okay, so that's what's caused that lag. So what we're going to do is we're going to pretend that that doesn't exist, and we're going to utilize the rest of the graph. Okay, what do we do with this graph? Well, you put your results from your experiment, your energy transferred and your temperature, and you need to calculate the gradient. Now for that you're going to need a ruler, and what you do is you get your ruler and you put it on your line, and you make sure that your ruler touches, well, if it's a completely straight line, like I'd hope it would be, this isn't so much of a trouble, but here just make sure that your ruler touches it at a single point, and you draw on a tangent like so. You then turn this into a right angle triangle like so. See, I told you this one was difficult. Lots and lots of different skills all at the same time. So you turn this into a right angle triangle. Okay. So to work out the gradient of a line, you need to do change in your y value divided by change in your x value. So x is this axis and y is that axis. Right, so let's work out our change in a x value. So this would be like you've got your triangle, and you read off from here and here to see how much the x value changed. So if this was like, I don't know, 20, and this came down at 47, you know that the difference between these 2 points here, you know that that is 27 joules. And again, what you do is you do the same thing with your other line. So you read across from here to the y-axis, and you go up here, and you read across to your y-axis. Just about fit it on. Brilliant. And then you look at the difference between those two, and if that was, I don't know, 10 degrees, and that was 57 degrees, then you'd know that the difference here between those two would be 47 degrees C. And then all you would do is you would do change in y would be 47 degrees, and the change in x would be 27 joules, and then you'd punch that into a calculator like so. So that would be 47 divided by 27 would come out as being, I don't know, 1.74. There you go. That'd be 1.774 degrees C per joule. Okay, the real value isn't going to come out as that. Those are just some random examples that I've put in. Except that there is a problem. Have you spotted what the problem is? If you look over here, what I've done is I've divided the temperature by the energy. If you look back up here to work out the specific heat capacity, seeing as we've forgotten all about the mass, seeing as it's just one, you've got to do energy divided by temperature. It's the wrong way round. So what you need to do to work out the specific heat capacity here is you need to do 1 over the gradient. And I literally mean you would be doing 1 divided by, in my silly example, 1.74. Okay? And that will output you a number, and that number is a specific heat capacity with a with a unit of joules per kilogram degrees C. Wow, what a long road it was to get here. Okay, maybe go and get yourself a cup of tea first before you try moving around too much, and don't operate any heavy machinery for at least an hour. Thank you.